All right, this will be the second video of 9.2, and this will just be covering remainder theorems. There's not an application of it quite yet until Taylor's series, so just keep this in mind. I'll just introduce the remainder theorems and where they come from, because it's not very intuitive, right? But unfortunately, there won't be much application up until we talk about analytic functions in Taylor's series. Yeah, so bear with me here. But you should be able to understand all the derivations that I make in this video. So, I don't actually think it's quite that useful, because I think we just end up using remainder theorems without even like knowledge of what came before. But in case you want to know where remainder theorems came from, this is the derivation. I spent like an hour and a half on this. Okay. All right, let's begin. All right, so we know Pn of x is some approximation for f, right? We can say this, right? And Pn of x, this is just some degree n polynomial, right? We're good here. Let's define the difference between Pn of x and f at x as some remainder, right? Because we know this isn't necessarily exact, right? So to make it exact, we'll have this function remainder. All right, so let's assume f is a C infinity function, right? Meaning it's infinitely differentiable on its domain, right? So this should be good. And let's investigate this one property of this. If we take the n+1 derivative of both sides, right, we end up with this. Now we know Pn is an n-degree polynomial, right? So we can represent it as like an times x to the n plus an minus 1 times x to the n minus 1, all the way to a0, like a1x plus a0, right? So we know the biggest term is just x to the n. When we take this derivative n+1 times, would you agree that we get 0? Right? Let's instantiate this with x to the 3. The first derivative is 3x squared. The second derivative is 6x. The third derivative is 6. And this n+1, 3 plus 1th derivative is 0. Right? Meaning that this actually ends up as this. So now we've actually found an equality between the remainder and the actual function, which is pretty cool, right? And now what can we do with this? Okay, so this will be kind of like I guess you could do this with MVT, but I'm going to do it a bit more intuitively, just because I think that would make more sense. First, let I be some finite interval on F's domain, yeah? We know F is continuous, right? So this is great. But this means on I, F has a min and max, yeah? This makes sense? And since f is infinitely differentiable, right, it also means it's infinitely continuous. Each derivative is continuous, right? So we know this derivative is continuous, this derivative is continuous, and we can go all the way to n+1, right? Okay, so now let's formalize this idea. So basically what we've said is that f, the n+1th prime derivative of f, has a min and a maximum on I, on this interval I, okay? So now we're gonna, also assume A is an I, okay? So this interval centered I. What we can write is that actually for every x, right, there exists a minimum and maximum, right? Where we have fn plus 1 is sandwiched in between. X is sandwiched in between, right? This should make sense, right? Because there's a min and max on I, meaning for any x in I, we have this, right? It has to be, there's bounds. Basically, we're saying for any derivative, right, on some interval, there's a bound for whatever values it can take for any x. Okay? Now, we also know this is true, right? So we know m is also less than or equal to r and x and m. These two are very, very important to know, okay? And we're going to do two derivations to get some equality with the remainder. All right? Let's take a look at this guy over here. We're going to integrate this guy from a to x, okay? In respect to x. Okay, well, you should agree that we can do this, right? And now, would you agree that we end up with Rn of n at x minus Rn of n at a, right? In the middle, and this is all less than or equal to m x minus a, less than or equal to big M x minus a, right? This should make sense. Now, Rn at a, let's see what we know over here, okay? We know that f at a is equal to Pn of a. Right, we know f prime at a is equal to p prime at n at a. And we know this all the way up until f at n at a is equal to p n at a. Which means that remainder is equal to 0, because these are equal at a. Does that track? This would track, right? This is the definition, right? We don't know how it is at the n plus 1th derivative, right? But we know at the nth derivative, these guys are equal, meaning the remainder has to be 0 at a, right? So this guy ends up being 0, okay? That should make sense. So now we end up with this, right? Now we integrate it again. All right, we're trying to get this term to just Rn. All right, so if we integrate again from a to x, right, at our dx is in here, we end up with m again, and we have x minus a squared over 2, right, less than or equal to, and now we have Rn minus 1 to the n of x, right? And we also have this, right? But this cancels out to 0, as we said before. So we end up ignoring him. And on this side, we also have this. And you can keep on doing this integration up until you actually just get Rn on its own. And you'll see that these are all less than or equal to m times x minus a to the n plus 1 over n plus 1 factorial. And on this side, we have x minus a to the n plus 1 over n plus 1 factorial. Okay, let's take a look at how exactly we got that, right? Because we see that here we start with the n plus 1th and we get to 0, right? Meaning we do this integration n plus 1 times, and every time we do an integration once, the degree of x minus a increases by 1, right? Because we can also write this as x minus a to the 0, right? And so we're adding 1 to this degree each time, and we do it n plus 1 times, yeah? So then our degree at the end should be n plus 1. And obviously the bottom is just factorials, right? This is 0 factorial, this is 1 factorial, this is 2 factorial, right? So we have this equality, right? And now we can take a look at this one. This one, let's just multiply both all sides by x minus a to the n plus 1 over n plus 1 factorial, okay? So we'll end up with this. It's less than or equal to f n plus 1. And if you have the remainder theorem next to you right now, you can kind of see the vision, right? We have a vision going on. Because now, right, what we have are two things bounded by the same number, okay? Or the same numbers. So now we want to see what we know about this. We know something about the function f to the n plus 1 derivative of x. This guy is always continuous, right? Because we know f at n plus 1 is differentiable, meaning it's also continuous. Note that if we defined c infinity as n plus 1, this would also work because c n plus 1 implies a continuously differentiable n plus 1 derivative, right? So we can also say that, but for simplicity, we'll just refer to it as infinitely differentiable. So since this is continuous, then by IVT, right, for any value in between here and here, we can find a value c such that this is equal to that, right? In other words, for every, let's say, n between these two values, right, this is just IVT, okay? IVT is pretty simple. There is a c between x and a such that fn plus 1 at c over n plus 1 factorial x minus a n plus 1 is equal to n. Great. This is what we know, okay? And you might be like, okay, what is the application of this? Well, it might ring a bell if I replace c with this bastard. And now this looks very familiar with the Lagrange's remainder theorem, right? But how does he apply? Okay, well, we know this is true, right? We know Rn of x is bounded by these two functions. Now we know that for any values in between these two, we can find a xi, right? So we know R of n is in between these values, meaning that we can say Rn is equal to this for some xi in between x and a. Oh my god, I really don't know how to do this. Okay. And this is our remainder theorem. So this was a derivation of Lagrange's remainder theorem. And nothing in here is actually exceptionally... actually, you could pretty easily formalize this proof, actually. I won't formalize it because, I mean, it's kind of, I mean... But this is sort of the idea, right? We only use EVT, we use integration, right? We use IVT. And we derive this result. And what does this result mean? Well, it just means that we can relate the remainder with our n plus 1 derivative of our function, right? And more specifically, I think this is a better way of thinking about it. The remainder is bounded by two things, right? And these two things have to do with the n plus 1 derivative, yeah? And so the remainder can only be so big on, like, for this function. And this basically just describes how accurate a function is. Because we know the limit as n goes to infinity of r n of x over x minus a to the n, if this equals 0, then we have a very good approximation. Would you agree? Because as the degree goes higher, right, if it outpaces this bottom term, we know it's a very, very good approximation. In fact, I think this is the definition of analytic, right? Meaning the Taylor series is straight up equal to the function. So that's very important. But now I want to introduce, because that's Lagrange's, I want to introduce another theorem called the integral remainder theorem. And so that proof should make sense. And now this proof is easier to understand, but more tedious, I would say, and less cool. But basically, all right, here's the derivation. We have f at x is equal to f at a plus the integral from a to x of f prime at t dt, right? This is just very standard, okay? That should make sense. And f, by the way, is our function we're trying to approximate, okay? All right, now we can do integration by parts over here. All right, let's let u, and keep in mind, we're integrating with respect to t, or deriving with respect to t, yeah? So we should have our u as f prime at t, right? Du is equal to f double prime at t, right? We have our dv is equal to dt, and let's set our v to t minus x, yeah? And we'll see why this is handy dandy in a very little bit. So then we have f at x is equal to f at a plus, and now we have our u times our v, but these are evaluated at the bounds a of x, and we subtract our integral from a to x of t minus x times du, so f double prime at t. Or sorry, or yeah. Sorry, I'm bugging out right now. Okay, there we go. And now let's expand this out just a little bit, and we can see something cool. So this guy is, by the way, we're evaluating this at t, yeah? So in fact, we can be a bit more specific here. T is equal to x, t is equal to a. All right, so first we have f prime at x, and x is a constant, by the way. Let x be fixed, right? So we're doing all of this in respect to some fixed x. And we'll see why that matters in a little bit. So now we have x minus x, right? Minus f prime at a minus x. And then this integral over here remains the same. And now we know this cancels to 0 because x minus x is 0. And x is a constant, right? X doesn't vary. Even if it did vary, this would still cancel to 0. And now we have f at x is equal to f at a minus this. But let's factor in the minus term into this, right? Let's change this minus, and let's factor in the minus into this a minus x. We're going to write this as x minus a. Right? So now we get f prime at a, x minus a. And now we have this integral once again. And now let's use integration by parts again. Let's have u as f double prime at t. We'll have du as f triple prime at t. We have dv as t minus x, right? And then v, here's the tricky part. We're deriving and integrating in respect to t, not x. So the antiderivative of t minus x in respect to t is t minus x squared over 2, right? Because we're doing this in respect to t. That's the key point. We don't chain rule with a negative x, because that's what we think of first, right? This took me like 10 minutes to figure out. Like I just looked at this for 10 minutes. I was like, why is the textbook saying it's not negative? But it makes more sense now. Okay, so now let's write this again. So now we have minus, and then let's have a u times t minus x squared times v, evaluated as t equals a and t equals x, subtracted by the integral of a to x. Well, let me move this guy. And we'll have our v and our du. And now if we expand this out, we have f at a plus f prime at a, x minus a minus, and then here, obviously, when t is equal to x, this will cancel to 0, right? So let's ignore the term. And so we have negative f double prime at a times a minus x squared over 2 plus this guy, right? And now these two negatives cancel out to positive. No. Oh my goodness. Positive, right? And since this is squared up here, we can manipulate the inside to be x minus a as well, and it'll end up being the same, right? So let's just do that. And boom, take a look at what we got now. And then we end up integrating again. And notice that when we integrate it, we'll always get positive signs for this term. And whenever we have a... And if you do it more, right? If you integrate this again, you'll have a minus x to the 3 over 6, right? And here you can't actually switch the negative signs, but that's okay because you'll end up having this being subtracted. And so when you change it to a plus, you can change these signs again. You can do the integration to see for yourself if you're curious, but if you can take my word for it, you can do that. And so if we do this enough times, we'll end up with f at x is equal to f at a plus f prime at a times x minus a, right? And this is all over 1 factorial plus f double prime at a times x minus a squared over 2 factorial, right? Plus f triple prime at a times x minus a cubed over 3 factorial. And we do this so many times till we get f at n at a times x minus a to the n over n factorial. And at the very end, we'll have this term. We'll either plus or subtract something. The textbook proves it by induction, but I really don't feel like doing that. And this term is f n plus 1 at a over n plus 1 factorial x minus a to the n plus 1. Or sorry, to the n. Yeah. Right, because, yeah. Okay, and now we see this is equal, right? This whole first part, right, is equal to the infinite, the finite sum of our power series centered at A. Right? And this is, okay, and something, sorry, this is, should be dt, and this is t minus x, yeah. Sorry, I miswrote it, because we're still integrating, right? And what we can do here actually is factor in the negative 1n into here, right? So now we can flip the sign of these two. So now we end up with just that. Okay, that should make sense. And now we have this term. Right? And this is all equal to f at x. So this is our Pn of x. And we see that this ends up being the remainder, actually. Right? Which is pretty cool, because we just showed that f at x was equal to these two terms together. This is equal to the nth polynomial. And the term we're left over with, we can set to the remainder, because that's what the remainder is left over with. So then we have Rn of x is equal to this remainder. How cool is that? Don't ask me about application. I have no idea right now. I'm sure there's an application. But yeah, boom. This is the second theorem, and we just derived it by through first principles. Look at that. And I think that's low-key it. I mean, there's a bit more in the textbook, but I feel like it's kind of like more nothing burgers when it comes to application, because I feel like, yeah, I don't think they'll ask this of us on the test or in the content, because their videos, right? Everything I just did today was like 8 times more than they did for the videos. And I'll go over more about analytic functions and all of that later. But yeah, so this is all like, I think this is nothing burger. I'll just leave it. But yeah, I just derived the 2 main remainder theorems. In fact, I only think they want us to know the very first one. This one's just kind of like a extra, I guess. So that's kind of a waste, but you know, boom, there it is. You know, remainder theorems.